Hi everyone, this is Adrian Jennings at Ubisense, and today I'm going to be talking about why IoT won't revolutionize the manual assembly line. So not as a failing of IoT, but just as a fact of IoT and what it does and what it doesn't do. So let's jump into this. And the first thing is, why is IoT interesting anyway? Why is connecting things up useful? And the answer really lies in the whole notion of Industry 4.0 and the strategy around the digital factory and sensorizing operations, right? So Industry 4.0, when you search about Industry 4.0, there's a lot of jargon and a lot of different ways of talking about it, but it really comes down to this notion of the cyber physical system, right? The idea that you can use computers to connect to and interact with physical process in order to give new insights and new flexibility and new efficiencies. So I have a definition of Industry 4.0, and that's this. That it means computers with sufficient understanding of and interactivity with the physical world, that they can help us plan and measure and manage and optimize and control and error-proof complex processes. Right? Complex processes are what we have to do better at. Planning, measuring, managing, optimizing, controlling, error-proofing, these are all the things that we care about. And if computers can help us do that, so much the better. And the important thing here is sufficient understanding, right? What does it mean for a computer to have sufficient understanding of the physical world and what's going on in our processes? And this is where we're going to see, we're going to start to see some of the edges of IoT. So let's start with a definition of IoT. And I kind of like this one. This is from Trend Micro. What is the Internet of Things? What do they say? They say the IoT can be described as an extension of the Internet and other network connections to different sensors or devices or things, affording even simple objects a higher degree of computing and analytical capabilities. That's quite a neat encapsulation. What is the IoT? It's extending the Internet to things, devices, connecting them up. And once you've connected them up, you can attach a lot of computing to those things. Actually, you can attach a lot more computing outside of the thing than you can fit inside of the thing. Think of a smart light bulb in your home and the stuff you can do because you can control it from outside because you're connected to it via the internet. Okay, so I like that definition, and that really helps us. And it's really about sensors and devices, right? About how that looks. One way of kind of picturing this is individual devices with sensors streaming data up into the cloud, say, and the focus is definitely on the devices and the tooling and the machines that have sensors fitted. And it doesn't necessarily need to be the cloud. It's a convenient way to think about it, and it's a popular way to talk about IoT. But IoT also means connecting to your connecting devices to your internal digital systems as well, to ERP and MES and SCADA and all those things. But it's very device-centric, right? It's a question of, it's very vertically linearized, right? It's data from devices up and down to a digital brain. For us, in a situation where we have fully automated processes, like if each of those devices is a machine executing a step in a process, then what helps us is the process flow is very simple. It's one machine to another. All of the interesting things in the process happen inside the machine. And so actually monitoring the machines is all you need to do. If you can, in an automated process, really understand what's going on inside your automation devices, then that really is the process. And this is where IoT has its magic, right? And anytime you listen to a presentation on IoT, you'll hear, one of the things that you'll hear in terms of what is the value, predictive maintenance is going to be high on the list of the things that everybody wants to talk about. Machines that self-monitor, predict issues, automatically call for maintenance. It dramatically decreases downtime, it decreases the cost of maintenance, improves the efficiency and so forth. And that is, you know, part of the magic of applying IoT to automated processes when the machines are the thing, right? So if we want to summarize that, we could say that for an automated process, the status of your process really is defined by the aggregated state of the machines that complete the tasks, right? If you knew everything about every individual machine and you aggregate that together, you add it all up, what you end up with is the end-to-end process, because everything that happens of any interest happens inside the machines. So IoT creates a very complete picture of the process by monitoring and controlling machine state, all to the good, and that's what it's for. But what I'm talking about here is IoT really going to revolutionize manual processes? So we look at manual processes and look at a situation where the things aren't the things doing the work. It kind of looks like this. This is the Embraer E190 assembly plant. And what is happening here is a lot of manual process, almost entirely manual process, including the guy driving the crane, right? There's a lot of movement, a lot of interaction, a lot of people. There are parts and tools and the product itself and the stands and the just inordinate number of moving parts that have to be synchronized in order for the process to work. And that's very different from an automated process. So here, in a manual process, the status of your process is not defined by the aggregated state of the machines. There really aren't that many machines. The state of your process is defined by the complex series of physical movements and interactions of people and tools and parts and products. And IoT doesn't see that activity. That's where IoT is actually blind. And so IoT does not have what I defined earlier as sufficient understanding of manual processes. It just doesn't see all those important bits. So if we have a look at a picture, you may actually have devices in your manual process that have some IoT connectivity. Your torque wrench may be feeding back torque results, and your forklift may be sending its state and state of battery charge and so forth. And whereas, you know, that's interesting, it doesn't define the entire process. The state of the battery on a forklift doesn't tell you whether it picked up the right load. Is it going to the right workstation? Is it taking the right route? Is it on time? All those things are about motion and interaction. And the reason is the process flow in manual process is really very complex and interconnected. Right? We're not moving through, let's say, a gear manufacturing process where we go through, you know, the grinding and hobbing and deburring and then heat treatment and then, you know, final finishing and polishing. That's a very linearized thing where everything happens inside the machine. In manual processes, we're talking about situations with a lot of interaction and moving parts, as I said before. So on top of the data that we're getting off devices, the IoT-like data, there's a huge amount more data that's coming off from the interactions. The orange lines and the orange data in this picture is all the stuff that IoT can't see, but it's all the stuff that's critical for understanding the state of the process, for being able to do things like predicting when a product will be finished, for example. So we have to do something more, and we can do something more. And that thing is called spatial intelligence. It's it's how you extend IoT into manual processes. If you think of the IoT as the Internet of Things, you have to add kind of this Internet of interactions, effectively, the digitization of all those moving parts. And that can be done. And it's done in layers, and let me explain the layers. And I've shown here at the bottom a typical plant, an aerospace plant in this case. This extends across any assembly process that has a high degree of manual content. So absolutely aerospace, absolutely commercial agricultural vehicles, for example, absolutely a passenger vehicle as well. Passenger vehicle assembly is linearized in a flow, but nevertheless, it is still made up of highly manual processes that involve the synchronization of a lot of moving parts. The products, the tooling, the people, the parts and materials, etc. So any kind of plant there at the bottom with a high degree of manual processing content, and at the top, add digital systems. And as I said, they may be our existing digital systems like MES and ERP. That may be on-premise, that may be in the cloud. It doesn't matter, it's this digital layer up there. And Industry 4.0, talking about cyber physical systems, we've got cyber at the top and physical at the bottom, and we have to connect the two. So there are a few layers that you need to instigate to connect those. The first one is to literally monitor the location, movement, and interaction of all the assets that you care about within the facility. This is the this is the green, not green, I apologize, the orange data that I talked about, the interactions between things. First thing to do is we need to put sensors on those. How do you sensorize an interaction? Well, you track the location of all the moving parts. You track a tool, you track a parts tote, you track the products themselves, and that, when you add that into IoT data, when you add that into, so for example, we have this tool, we know that it just returned a torque of 5 Newton meters, but where is it? What workstation was it in? What product was it working on? That context is what you add when you figure out the location of the tool. And the location of it within the facility, right? So that's the first thing, location sensors, and there are a variety of different versions of that, different technologies that apply in different cases. But once you have that, it's a huge amount of data, way too much to really to process yet. You go to the next level, which is to say, look, out of all that data, a lot of it's not very interesting, actually. Who cares about the location of a tool sitting on a bench? And what I care about is a tool moving into a workspace or into a process zone in a product. So the next level is to take all that data and turn it into events. And that requires a spatial model, and this is where we get into what I mean by spatial intelligence. Here we have to model the plant not in terms of objects and walls and conveyors, but here's a workspace and there's a workspace and here's a storage space and here's a kitting area and so on and so forth. So when we kind of draw those geofences, we can pull out events like this product has just entered inspection cell 3. This part has just been delivered to dock door number 5. So those are events, those are the things we care about, and now we have a very structured set of data that is telling us what's going on in the process. In fact, what we've developed there is the spatial intelligence part of the system, but there's one more level which starts to add on top of that the true business value, and that is a logic layer which enables you to program this platform with what is our expectation, what's the plan, what does good process mean, what is supposed to happen. And with that model in there, comparing with the real-time events, you can start to detect issues and anomalies and communicate those up to the cyber part of our cyber physical system, the digital systems. And that allows our digital systems to get a view of what's going on, what's going wrong, and gives them the real-time ability to react and compensate for processes going off plan. It also has digitized the entire process, and now that the processes are completely software defined, it also gives you a huge amount of flexibility in how those processes should run. So once you've been able to communicate those issues and errors up, that allows either digital systems, or more commonly people, managers and supervisors, the ability to intervene and correct. It keeps everything flowing exactly on plan. And we've taken from the bottom this giant complexity of manual process, digitized it in the blue layer, in the next layer up, pulled out the important events that we care about, in the next layer up, monitored those events for which ones we really need to pay attention to, and then communicated up to the systems or people that can step in and make a difference. And that level in the middle there, those layers of digitizing the process and monitoring against plan, that is what I mean by spatial intelligence. And there is a software platform called a spatial intelligence platform that does this in the same way that IoT does for devices. IoT monitors the state and status of things, and a spatial intelligence platform measures the state and status of interactions and processes. And it captures those interactions that IoT doesn't see. So that fills in the missing blank, right? That is how you extend IoT into manual processes, is you add this spatial intelligence layer, and that illuminates and connects and digitizes those manual processes. So that's conceptually what it is. What does it do in practice? I'm going to run through here some examples of actual use cases where spatial intelligence is making a difference. Before I do that, though, let's talk a little bit about categories of manual process errors, because really there are only 5 different common ways for manual processes to go wrong. There are probably a bazillion ways for an automatic process to go wrong, because there are many different ways a machine can fail. But in terms of manual processes, us doing things, there are really 5 categories. So there are location errors, which are things being in the wrong place. And we're going to run through each of these here, and I'm going to give you some examples in practice. So things in the wrong place. You can probably think of tons of examples from your own experience where that has occurred. 2 or more things interacting that shouldn't be. That's an interaction error. There are count errors. Too few things or too many things in a certain place. And we'll talk about some of those examples. Errors of duration. A task that's taken too long, hasn't taken long enough. Too long between tasks. And the final category is sequence, things happening in the wrong order. And I think it's possible to trace pretty much all manual process errors to one of these things. And you can see how none of these things are really visible to IoT, but how they become completely illuminated with spatial intelligence. So let's have a look first at the first category, which is the category of location errors, things in the wrong place. Now, I'm not going to dive super deep into each of these, just in the interest of time. But I am going to go through a few of them, and I'll give you a link at the end here where you can delve a bit deeper and go through a few of these. So let's look at some examples. I'm going to start down here at the bottom left, and choose just a simple example of a tool being used in the wrong workstation. And that could be any kind of tool. That might be just a simple hand tool. It might be a highly complex, DC nut runner. And anything in between. But a tool being used in the wrong workstation is often a compliance issue, often a quality issue, and sometimes a safety issue as well. And in some cases, tools are completely untethered to roam the shop floor. In some cases, they're more tethered. Think of auto assembly, where there is physical tethering of tools in a lot of instances. But more and more, the move there is actually towards cordless tools anyway. So even those tools that are tethered today are becoming untethered quickly as we move forward. So a location error would be using a tool in a wrong workstation, in the wrong process, on the wrong product. And I know you can think of a lot of examples where that happens. So obviously that's a simple thing to understand and manage if you know the location of the tool and the type of tool, and you know it moves into a workstation, and you know from the location of the product in the workstation what the product is supposed to be, and you know from the ERP, the process that's supposed to be executed, you can make a determination whether that tool is the correct one for the job automatically. And if not, then you flag that up to people who can make a difference. In this case, you may page a supervisor. You may tell the worker themselves that's the wrong tool. You may be able to disable the tool wirelessly and prevent the tool being used in the wrong workstation. So a simple example, spatial intelligence, big concept, but very down-to-earth problem and solution there. So think about a part being delivered to a wrong workstation. A little bit hard to do in an automotive, maybe. Pretty straightforward to do in, let's say, aerospace, particularly in aerospace where tasks travel forward. This is something that's not common in higher volume situations, but a set of tasks in one workspace that hasn't been completed can be finished off somewhere else. And so the tasks do dynamically move around. And obviously, parts being delivered to the wrong place is an issue and something that's going to slow down the process. Someone's going to have to go hunting for those now when they need them. Sticking with parts, think of parts coming in and flowing in, and a trailer being at the wrong dock door, for example. And dock door management can be quite complicated. It's highly dynamic, and understanding where the trailers are, what's in the trailers, where they're needed, where they're being delivered. It's simple to alert the driver that he's gone to the wrong place or picked up the wrong trailer, for example. So again, just trying to give you an idea across the assembly process where things being in the wrong place can cause issues and delays. If we move to the category of interactions of things, then the last one I'm talking about, a thing being in the wrong space. Now I'm talking about two things being together that really shouldn't be. So lots of examples here, and let me just pick a few again. Let's start with, since we started with tools in the last time, let's talk about tools this time as well. We talked about a tool being pulled into the wrong workstation. That's a location error. But a tool being used on the wrong product with the wrong settings. That's an interaction error. Maybe it's in the right workstation, but it's set up incorrectly for the product that's in the workstation. So the interaction between the tool and product is incorrect. So that's kind of like a location issue, but now it involves objects together. Moving back into logistics again, in a situation where kitting is occurring, a part being placed in the wrong kit tote is an incorrect interaction between a part and the tote. If that mistake is made, the kit gets delivered and suddenly we have the wrong parts out on the shop floor. And again, we have delays and potential errors because of that. Easily prevented by detecting that right at the source, understanding that's incorrect interaction, the parts going in the wrong bin. Again, in logistics, I talked about this earlier on. An IoT monitoring of a forklift might tell you how the forklift is doing, but is it telling you whether it's doing the right thing? So, for example, picking up the wrong pallet. You've been dispatched to get, a transmission of type A, and you pick up a transmission of type B. And finding that error early is the best way to keep the process moving. And in fact, if I know the location of the forklift and the location of the pallets, and I know from the ERP which one, or maybe it comes through the MAS in this case, which pallet it's supposed to be picking up, I immediately know when the forklift has picked up the wrong pallet, and I can tell the driver, put it back down, move one space to the left, that's the one you're supposed to be getting, and prevent that incorrect delivery. So once again, a very simple interaction example, very powerful. So problems of count, too few or too many things. These are probably quite obvious in some cases and not in others. Let's continue our trend of starting by talking about tools. The number of fastenings that have been completed for a part. Let's say a cylinder head with 12 fasteners and only 11 have been completed. That is an undercount, and that is incorrect. And we can count that by the movements of the tool. We can also, in that case, count it by the number of torque readings we've had, but can we guarantee that all those torques came from separate bolts? And the answer is no. You need to monitor the location of the tool to know that it's got 12 torques off 12 individual bolts. So that's a kind of a micro view on location and spatial intelligence. A bigger issue, bigger physically sized issue is a workstation being empty. That's a count of 0, where in an efficient plant maximizing throughput, all workstations would be filled at all times. And that sounds odd to people who are thinking about an automotive assembly line, but it's not odd at all if you think about non-linear processes, particularly in repair and rework, or an entirely non-linear manufacturing process, more like a low volume aerospace type of situation. When a product has been moved out of a workspace and that workspace is available, the most efficient way forward is to make sure that it's filled and 100% utilized. So a count of 0 is a problem in that case, and something that somebody needs to know about. A parts buffer running low, that's a very common one, particularly in high volume, right? Having the number of parts in a line side buffer dip below a certain level is certainly an indicator of risk and potential line stoppage, and now obviously we're talking about automated Kanban. But it's a spatial intelligence problem, right? What does Kanban mean? It means, getting the parts to the right place at the right time, and that is a count problem in a particular space. How many parts are in this space? What is the rate they're being depleted? How can I predictively dispatch a replenishment? So an old problem, but think of it in terms of spatial intelligence. Duration. Now here's a problem plaguing any lower volume process, medium to low volume. Again, it's kind of hard to take too, well, it's not hard to take too long on an automotive assembly line, but it's a big problem if you do. It's very easy to overrun task durations in repair and rework. It's very easy to overrun task durations in very long takt time processes. And very long, it doesn't even need to be very long. Given 20 minutes of takt time, it's quite easy to run over by 2 or 3 minutes. Given several hours of takt time or even days of takt time, it's possible to overrun by quite a long mark. So these are problems of duration. Down in the bottom right, the primary duration issue is just a process step overrunning. Processes getting off pace, and particularly imagine you have 2 hours to do a set of tasks, and an hour and a half in you might find out that you're hopelessly behind, and there's no chance of finishing on time. Well, obviously that affects throughput for the entire line behind you, but it's something that you can easily detect with spatial intelligence as you understand the interactions within that process and whether they're as planned. A task not started yet, not overrunning necessarily, but just starting late. And again, another common issue in terms of scheduling, and another way that the overall cycle time in any given process can be longer than it should be, and that really hits your throughput. And then a product that's remained between process steps too long. This is a problem that we solve all the time. How do you make sure that stuff doesn't just get forgotten between steps? And again, that sounds a bit daft to some people in higher volume, but the low volume assemblers out there know full well that it's quite possible for products to get stuck between steps. So the final, and this is pretty straightforward and obvious, the final matter of sequence, are things happening in the right order? Tradition in these is to start with tools, so let's go back to the cylinder head and our 12 bolts, and maybe we know that the count was correct, but do we know they were done in the right sequence? There's a really important fastening sequence. It's a high pressure sealing surface. They need to be done right. And monitoring the location and movement of the tool from one step to the other, the sequence of events, is what tells you whether that was done correctly. The logistics, staging parts kits in the right or wrong sequence, another sequence issue to worry about. And then, products repeating a process step. That happens quite often. Let's say the car goes through rolling road and it fails underbody inspection, it gets repaired, it comes back, it's supposed to go to underbody and it gets put back to rolling road by mistake that it's already passed. And that can cause, obviously, throughput issues as well. So all kinds of issues of sequence that we have to worry about too. So that's where I'm really coming from. Why won't IoT revolutionize manual assembly? Well, because it can't see manual assembly. The process is not described by the status of machines. And what IoT sees is the status of machines. It cannot see all the things that we just talked about. All those things are issues of interactions. It won't revolutionize manual assembly because it can't see the orange lines here. It can't see the counts and the durations and the interactions and the sequences and all of the things we just talked about, which are the bane of manual process efficiency. And that is what you can do by adding this extra piece alongside IoT, this notion of spatial intelligence, which you can think of as adding to the Internet of Things, this notion of kind of the Internet of interactions, effectively. So that's why IoT won't revolutionize manual assembly. It just can't see it. Spatial intelligence platforms absolutely see into those processes, and that's how you digitize manual assembly, and that's how you reap all the benefits of IoT in those industries that have a high manual content. So that's it from me. Thank you for listening. There's a website link here. You can delve more into other kinds of use cases for spatial intelligence at ubisense.com. And of course, at any time now or in the future, I'd be happy to answer any of your questions, and my contact details are right here. So thank you.